The solar system feels permanent because the rhythms are dependable. Planets rise into the night sky on schedules that predate human memory, and the sun's pull seems like a law written into the background of reality. Yet the solar system is not sealed. It is a busy neighborhood inside a galaxy where stars orbit the center of the Milky Way, passing other stars at distances that are enormous by human standards, but close enough over long spans of time for gravity to reach across the gap. In that wider environment, there exists a class of worlds that do not belong to any star at all. A rogue planet is a planetary mass object that travels through interstellar space without being bound to a star's gravity. Bound here means locked into an orbit, on the repeated looping path created when an object's speed is not enough to escape a larger body's gravitational pull. A rogue planet is free of that loop. It is a traveler. How could such a world exist? Evidence suggests more than one route. Some may form around young stars and later be thrown out during the violent reshuffling that happens when giant planets migrate and tug on one another. Others might form in isolation, collapsing out of a cloud of gas without ever igniting as a star, then cooling into a dark, massive sphere. Observations have hinted at free-floating planets through techniques that catch their presence indirectly, and theoretical work indicates that planet ejection during early system formation should not be rare. But the exact number of rogue planets in the galaxy remains uncertain. It depends on assumptions about how often planets form, how often systems become unstable, and how well our instruments can detect cold, faint objects drifting far from any sun. In other words, we know these wanderers can exist, and we have reason to suspect there are many, but the census is still incomplete. Now imagine one of them entering our solar system, not crashing dramatically into the sun in a blaze, not arriving with a roar, but sliding in on a trajectory that was set long before life began on Earth. In the cold between stars, it would be almost invisible. A planet without a star does not shine with its own light. It can reflect light, but interstellar space offers little to reflect. It can emit heat, but a world that has spent millions or billions of years away from any star will have cooled. Unless it is still warm from formation or warmed internally by radioactive decay or tidal flexing, it is mostly a black object against a black background. If it is far away, it is not a bright dot. It is a missing piece of the sky. So the first question is not, what happens when it arrives? The first question is, how would we know it is coming? In space, gravity is the messenger. A planet approaching the solar system would announce itself through its effects on other bodies long before anyone sees it directly. This is not a mystical influence. Gravity is a force that acts at a distance, and while it grows weaker with separation, a sufficiently massive object can still create measurable changes. Those changes would be subtle at first, the kind that appear as tiny mismatches between prediction and reality. Astronomers track the positions of planets, moons, and spacecraft with astonishing precision. They know where Mars should be to within a small fraction of the planet's diameter. They track spacecraft by radio signals and measure their speeds and positions by the timing of those signals. If an unseen mass begins tugging on the solar system, the first clues might show up as anomalies in these measurements. A spacecraft arriving slightly early, a planet drifting a little off its expected path, the long-term timing of a distant object's orbit slowly shifting. Yet, the solar system is already full of gravitational complexity. The planets tug on each other. The sun is not perfectly still. It wobbles as the planets pull on it. The asteroid belt contains countless bodies with their own tiny influences. Far beyond Neptune, there are objects in the Kuiper belt, a region of icy bodies orbiting past the outermost major planet, and still farther out lies the Oort cloud, a vast reservoir of comets loosely bound to the Sun. Even the Milky Way's gravitational field exerts a gentle tug, and passing stars disturb the outermost fringes over time. In that noisy environment, isolating the fingerprint of a rogue planet would be a detective problem. The most likely early hints would come from the outskirts, where orbits are slow and fragile. Consider an object far beyond Neptune, where sunlight is weak and orbital periods are measured in centuries or longer. Out there, the Sun's grip is still dominant, but the system is more sensitive to intrusions. A rogue planet passing through could tilt the planes of orbits, stretch them into more elongated shapes, or cluster certain orbital orientations through gravitational shepherding. Elongated here refers to eccentricity, a measure of how stretched an orbit is compared to a circle. A perfectly circular orbit has low eccentricity. A long, narrow orbit that dives close to the Sun and then swings far away has higher eccentricity. If a rogue planet approaches on a path that brings it near those distant bodies, models indicate it could alter their eccentricities and inclinations, where inclination is the tilt of an orbit relative to a reference plane. Those changes would not necessarily cause immediate catastrophe, but they would be the first ripples spreading inward. Meanwhile, the rogue planet itself would be moving. The key variable is speed. A rogue planet is not coasting gently, like the planets that share the Sun's orbit around the galaxy. It could be moving fast relative to the Sun, perhaps tens of kilometers per second. Its trajectory would be a flyby unless it loses energy somehow, because capture into a bound orbit around the Sun is difficult. Capture requires that the intruder shed speed. In space, there is almost nothing to slow it down. Without a mechanism to dissipate energy, such as a close interaction that transfers energy to another body, or a rare encounter involving multiple gravitational exchanges, the most probable outcome is a hyperbolic passage. The rogue planet comes in, swings around the Sun, and heads back out to interstellar space. Hyperbolic here describes a path that is open, not closed, meaning it does not repeat. It is a one-time visit. One time does not mean harmless. Even a flyby can restructure a system if the encounter is close enough or the intruder massive enough. Imagine the solar system as a delicate choreography. Each planet follows a track shaped by the Sun and by the gentle pulls of its neighbors. For billions of years, this choreography has remained stable enough for life to evolve. But it is stable in the way a mountain slope can be stable. The snow holds until an extra vibration triggers an avalanche. The rogue planet would be that vibration, and the question becomes, how close does it pass? How massive is it? And which bodies does it disturb most strongly? Mass matters because gravity scales with it. A planet the mass of Earth would be significant, but a planet the mass of Neptune or Jupiter would be transformative. Distance matters because gravity weakens rapidly with separation. If the rogue planet passes far beyond the Kuiper belt, the solar system might barely notice. If it passes through the outer planetary region, the effects could cascade. If it dives into the inner solar system, close to the orbits of the terrestrial planets, then we are in a realm where catastrophe is not a cinematic exaggeration, but a scientific possibility. Yet even before we reach that dramatic inner scenario, there is a middle ground where tension builds. The outer planets are giant reservoirs of momentum and gravitational influence. Jupiter in particular acts like a gatekeeper. It shapes the paths of comets and asteroids, sometimes shielding Earth by deflecting them, sometimes sending them inward by altering their orbits. A rogue planet interacting with Jupiter would be like adding an unexpected dancer to the center of the stage. The gravitational exchange could change Jupiter's orbit slightly. That slight change could shift resonances, the gravitational rhythms that occur when orbital periods have simple ratios. Resonances are not mystical harmonies. They are repeated tugs at the same point in an orbit that can add up over time, like pushing a swing at just the right moment. In our solar system, resonances sculpt the asteroid belt and influence the stability of small bodies. If a rogue planet perturbs the outer planets, those resonances could move, destabilizing populations of asteroids and comets that have been parked in stable niches. This is where the approach of a rogue planet begins to feel less like a single event and more like a chain reaction. The intruder does not need to hit anything to cause impacts. It can rearrange gravitational pathways so that other objects, long dormant, begin to wander. A comet from the Oort cloud, barely bound to the Sun, can be dislodged by a small perturbation. It may take thousands or millions of years to fall inward, but once its orbit is altered, the timer has been set. That is why in planetary science consequences are often delayed. The trigger and the damage can be separated by timescales that dwarf a human lifetime. Still, some effects could be immediate on astronomical timescales, meaning years to centuries. If the rogue planet passes through the region of the giant planets, it can scatter smaller icy bodies inward quickly. A scattering event is a gravitational slingshot, where a small body gains or loses energy and is flung onto a new orbit. Those new orbits can intersect the paths of planets. If enough small bodies are redirected, the inner solar system could experience an elevated impact rate. Not a guaranteed apocalyptic bombardment, but a statistically increased hazard, the kind that would show up as more near-Earth objects, more long-period comets, and more opportunities for collisions. Even if no impacts occur, the planets themselves could be nudged. A nudge in space is not a push that stops. It is a change in velocity. A planet shifted slightly onto a different orbit will keep that new orbit unless another force changes it again. For Earth, the most sensitive parameter is not just how far we are from the Sun at one moment, but the shape and tilt of our orbit over long periods. Earth's climate is influenced by slow variations in eccentricity, axial tilt, and precession, the wobble of Earth's rotational axis. These cycles are driven by gravitational interactions with other planets, mainly Jupiter and Saturn. If a rogue planet modifies the orbits of the giants, it could indirectly alter Earth's long-term climate cycles. The magnitude of this effect is uncertain and depends strongly on encounter geometry. But the mechanism is clear. Change the gravitational architecture of the system, and you change the parameters that modulate sunlight over geological time. At this stage, with the rogue planet still far away, the documentary camera would not be aimed at a glowing object. It would be aimed at the precision of measurements. The tension would come from a mismatch between prediction and observation, an uncomfortable gap that widens as more data arrives. Astronomers would rule out instrument errors, refine models, account for known bodies, and still the anomaly would remain. There would be debates, competing hypotheses, and gradual convergence as the invisible cause becomes harder to deny. The public would hear fragments, a slight irregularity in a spacecraft trajectory, a puzzling shift in the orbit of a distant icy world, a statistical clustering that does not fit the old map. None of it would sound like a doomsday headline. It would sound like the solar system has developed a faint limp. Then, eventually, the intruder would be seen. Detection would likely come from infrared surveys, because a cold body emits most of its heat in infrared wavelengths, light beyond what human eyes can see. Modern astronomy uses telescopes that scan the sky in these wavelengths to find brown dwarfs, cool stars, and faint objects. A rogue planet would appear as a moving point, a shifting position against the background of distant stars over days and weeks. Its motion would distinguish it from everything fixed. Once it is seen, its orbit could be calculated. The calculation would not be perfect at first. It would improve as more observations refine the trajectory, shrinking uncertainty. In those first weeks, the crucial question would be whether the path intersects the realm of the planets, and if so, how closely. If models indicate a distant passage, the solar system's response might be limited to the outskirts. If models indicate a closer flyby, then every new observation would carry weight, because a tiny change in the estimated trajectory could mean the difference between a harmless swing through the far outer regions and a passage that grazes the domain of Neptune, Uranus, Saturn, or Jupiter. When the solar system is vast, but the distances between orbits, in gravitational terms, can be narrow corridors where interactions become abrupt. Now, the premise sharpens. What happens if a rogue planet enters the solar system in a way that brings it close enough to matter? The first impacts of that mattering would not be impacts at all. They would be rearrangements. Orbits would shift first in the outer regions, then through the intermediate zones. A rogue planet would begin by stealing attention from the Sun's gravity, competing for control over small bodies. Some objects would become temporary satellites, captured for a time into orbit around the intruder, then released. Others would be flung outward, becoming rogues themselves. Some would be sent inward. This is the beginning of a cascade, and it is where the film transitions from detection to consequence. Because once the intruder's path is known, the solar system becomes a set of targets. Not targets for collision, but targets for gravitational interaction. Every planet has a sphere of influence, the region where its gravity dominates over the Sun for nearby small bodies. The rogue planet would carry its own sphere of influence, sweeping through the solar system like a net. And as it approaches the realm of the giant planets, the next question becomes unavoidable. Which worlds will it disturb first, and how will those disturbances propagate toward us? That is the bridge into what comes next, where gravity stops being a distant clue and becomes an active sculptor, turning small anomalies into the first true casualties of a system suddenly forced to share its space. Once the rogue planet is no longer a distant suspicion, but a calculated trajectory, the solar system stops feeling like a set of independent worlds and starts behaving like a connected machine. That is the uncomfortable truth about gravity. It does not respect categories. It does not care whether a body is a planet, a moon, an asteroid, a spacecraft, or a cloud of ice the size of a city. If mass is present, gravity couples it to everything else, and those couplings can transmit change across enormous distances. The first casualties of a rogue planet's arrival are rarely the ones people imagine. Not oceans boiling, not mountains cracking open, not a sudden eclipse that never ends. The first casualties are expectations. The solar system has been mapped with exquisite confidence. And that confidence is based on the assumption that there is only one dominant architect, the Sun, with the planets as long-term tenants. Introduce another architect, even briefly, and the rules of prediction begin to fail in places that were once quiet. Out beyond Neptune, quiet is a relative term. This region is populated by icy bodies left over from the solar system's formation, many of them small, some surprisingly large, moving in slow orbits where a single revolution around the Sun can take centuries. Their paths are stable not because they are protected, but because the gravitational environment is gentle. The Sun's pull is weaker there than in the inner system, and the planet's influences arrive as distant nudges rather than sharp kicks. That gentleness is exactly what makes the region vulnerable. When a new mass moves through, it does not need to break anything. It only needs to tilt a few trajectories. As the rogue planet approaches, its gravity begins to compete with the Sun's for control of these distant objects. The mechanism is straightforward. Gravity changes velocity, and velocity determines orbit. A tiny change in velocity, applied at the right time, can stretch an orbit into a more elongated shape, lift it into a new plane, or shrink it inward. In the outer solar system, where orbital speeds are lower, it takes less change to produce a meaningful result. Models indicate that a close passage could scatter outer bodies in all directions, like a hand disturbing a field of slow-moving debris. Some would be flung outward, gaining enough speed to escape the Sun's gravity entirely. Others would be pushed inward toward the giant planets. A third group would be captured temporarily by the rogue planet itself, circling it for a time before being released as the intruder moves on. Temporary capture sounds almost gentle, but it is one of the ways a rogue planet can create lasting change without ever touching anything. When a small body is captured, it exchanges energy and momentum through complex gravitational interactions. When it is later released, it does not simply resume its old orbit. It leaves with a new speed and direction, and the solar system's architecture has one more altered component. Multiply that by thousands or millions of small bodies, and the intruder's passage becomes not a single disturbance, but a restructuring of the outer population. The most immediate danger, however, is not the loss of distant icy bodies into interstellar space. It is what happens when a portion of them are redirected inward. The outer solar system acts as a reservoir. The Oort cloud, a vast shell of comets loosely bound to the Sun, is so far away that a passing star can perturb it. A rogue planet entering the solar system would be closer and more massive than most stellar passers-by that influence the cloud, depending on its trajectory. A gravitational perturbation there can dislodge comets, and once dislodged, those comets begin long, slow falls toward the Sun. The time delay matters. A rogue planet could pass and leave, and only later, long after the sky has returned to normal, the inner solar system could begin to see the consequences in the form of new long-period comets arriving from far beyond the planets. If the rogue planet's path takes it not through the far outskirts, but closer to the giant planets, the time delay can shrink dramatically. The region around Uranus and Neptune contains many smaller bodies whose orbits can be altered into intersecting paths in relatively short astronomical time. When such a body is thrown inward, it does not have to travel from the edge of the Oort cloud over millions of years. It can enter a new orbit that brings it into the realm of Saturn or Jupiter within decades or centuries. Once that happens, the solar system's internal machinery begins to amplify the disturbance. Jupiter is the amplifier. Its gravity is powerful enough to reshape the orbits of comets and asteroids during close encounters, redirecting them either outward or inward. A rogue planet that perturbs the supply of icy bodies and sends more of them toward Jupiter effectively increases the number of gravitational encounters in the system. Each encounter is a chance for a comet to be thrown onto an orbit that crosses Earth's path. That does not mean impacts become certain. Space is enormous, and most crossings miss, but it does mean the probability landscape changes. If the number of Earth-crossing objects rises, then even without a guaranteed collision, the risk increases. The solar system becomes a busier shooting gallery, not because the rogue planet fires anything, but because it rearranges the trajectories of objects that were already there. There is another pathway to danger that is quieter but potentially more profound: the rogue planet's interaction with the planets themselves. Planets are massive, and massive bodies do not get tossed around easily, but they do not need to be tossed to matter. A small shift in a planet's orbit can change the gravitational resonances that structure the solar system. A resonance, defined in plain terms, occurs when two orbital periods form a repeating ratio, so that gravitational pulls occur in a regular pattern. That regularity can either stabilize or destabilize depending on the geometry. In the asteroid belt, resonances with Jupiter create gaps where asteroids are removed over time. In other regions, resonances can trap objects into predictable configurations. The solar system is threaded with these patterns. If the rogue planet passes through the outer system and nudges the orbit of a giant planet, it can shift the locations of resonances. A resonance moved by even a small amount can destabilize bodies that were once safe, or stabilize bodies that were once chaotic. Either way, the distribution of small objects changes, and that redistribution can feed the inner system with new hazards. Now consider the chain of cause and effect as it unfolds. A rogue planet approaches. Its gravity first disturbs the outer small bodies. Some of those bodies are redirected inward. That increases the traffic of comets and icy objects into the realm of the giant planets. Jupiter and Saturn, through their own gravity, then scatter a portion of those objects further inward. Some become short-period comets, returning again and again. Others become near-Earth objects, crossing the orbit of our planet. Even if Earth escapes direct impact, in the inner system becomes dynamically hotter, more close approaches, more potential for collisions with moons, more dust produced by fragmentation, and more material redistributed across space. Dust may sound minor, but dust has consequences. Increased dust in the inner solar system can alter the brightness of the night sky, create more frequent meteors, and over time contribute to a haze that subtly affects sunlight. The magnitude of such effects depends on how much material is injected, how long it persists, and how quickly the dust is removed by radiation pressure and planetary sweeps. Radiation pressure is the gentle push of sunlight on tiny particles, and it can expel dust from the inner system. But if the rogue planet triggers a sustained increase in comet fragmentation, the dust supply could rise for long periods. This is not a guaranteed climate catastrophe, and responsible language matters here. Evidence suggests that large-scale changes in dust environments can influence planetary climates, but the extent would require detailed modeling for a specific scenario. What is credible to say is that dust is part of the cascade, another thread connecting gravitational disturbance to environmental change. The planets themselves can also be affected in ways that are not immediately visible but unfold over long time. If a rogue planet passes close enough to a giant planet, it can alter that planet's orbit. The change might be tiny in absolute terms, but over millions of years, small changes can shift the timing of orbital interactions among planets. Earth's long-term orbital variations, which modulate the distribution of sunlight across latitudes and seasons, are influenced by the gravitational pulls of Jupiter and Saturn. A slight alteration in the configuration of the giants could modify the patterns of Earth's eccentricity and axial dynamics. That is not a claim that a rogue planet would instantly freeze or fry the planet. It is the more subtle and, in some ways, more unsettling possibility that the intruder could rewrite the long-term background conditions under which climate cycles operate. At the same time, the solar system has a history of resilience. It has endured close stellar passages, the migration of giant planets early in its life, and countless smaller perturbations. So where is the line between disturbance and disaster? The line is drawn by proximity and mass, but also by timing and geometry. A rogue planet that passes far outside the planetary region may mostly shake loose comets from the outer cloud, creating a delayed increase in cometary arrivals without significantly perturbing planetary orbits. A rogue planet that passes through the realm of Neptune and Uranus could cause significant scattering of icy bodies and perhaps alter the outer planet's orbit slightly. A rogue planet that passes close to Jupiter or Saturn could do more, because those planets are central hubs in the solar system's gravitational network. The most dramatic scenarios occur when the rogue planet's trajectory brings it into a region where gravitational encounters become close enough for strong exchanges of energy and momentum. Those exchanges are not merely pushes, they are trades. When two massive bodies pass near each other, they can exchange orbital energy in a way that changes their paths. The smaller body experiences a greater change. That is why comets can be flung into new orbits after a close encounter with Jupiter. But if the intruder is itself massive, the planet it passes can also be altered. The result can be a slight change in the planet's distance from the Sun, its orbital eccentricity or its inclination. A change in inclination, the tilt of the orbital plane, can be particularly disruptive because it can alter the relative geometry of the entire system. Planets that once orbited in nearly the same plane could begin to diverge, increasing the likelihood of close encounters over long time and adding an element of dynamical instability. This is also where capture becomes a possibility worth discussing, not because it is the most likely outcome, but because it is the scenario with the most enduring consequences. For a rogue planet to be captured by the Sun, it must lose enough speed that its trajectory becomes bound, turning from a one-time hyperbolic path into an elongated orbit. In most cases, there is no easy way to lose that speed. Space offers no friction, but gravity can facilitate energy transfer if the intruder passes through a region where complex multi-body interactions occur. For example, a close encounter involving one of the giant planets could transfer energy from the rogue planet to the planet, or vice versa, changing the intruder's trajectory. Such a capture would likely require an arrangement of timing and geometry that is uncommon, and models indicate capture is generally rare compared to flyby. Still, rare is not impossible, and if it happened, the solar system would acquire a new member on an unusual orbit, likely far more elongated and inclined than the planets we know. A captured rogue planet would keep stirring the system each time it returned near the planetary region. A single flyby is a wound that can heal into a new equilibrium. A bound intruder is a chronic condition. Even without capture, the flyby itself can leave a signature that persists. If the rogue planet strips away parts of the outer small body populations, the solar system's distant reservoir is diminished. If it sends an influx of comets inward, the inner system could face a long interval of elevated impacts and close approaches. If it perturbs planetary orbits, the long-term stability landscape shifts. None of these outcomes require cinematic exaggeration. They follow from gravity's basic rules. So by the end of this phase of the encounter, the solar system is no longer waiting to see what the rogue planet is. It knows. The question becomes more personal. What does the intruder do to the pathways that connect the distant cold to the inner warmth? And how fast can those pathways deliver consequences? Because the moment the rogue planet's influence begins to move Jupiter's resonances, and the moment small bodies begin to cross the invisible boundaries between stable regions and chaotic ones, the dynamics stop being slow background astronomy. They become a countdown measured in orbital periods, and that countdown leads directly to the next escalation. The point where orbits themselves, once reliable, begin to behave less like tracks and more like wagers, with outcomes that depend on tiny differences amplified over time. But there is a moment in every gravitational encounter when the language of certainty starts to fail. Not because physics stops working, but because the system becomes sensitive in a way that feels unfamiliar. Before the rogue planet arrives, the solar system is mostly predictable. If you know the positions and speeds of the planets well enough, you can project their motions far into the future. There are small uncertainties, but the architecture is stable, and stability is what makes long-term prediction meaningful. As the intruder closes in, stability can turn into something that looks similar but behaves very differently. The solar system can enter a regime where small differences in timing and distance change outcomes dramatically. This is the territory of chaotic dynamics, which does not mean random motion. It means motion that is highly sensitive to initial conditions. A tiny shift in a planet's position at the moment of closest approach, a slight difference in the rogue planet's speed, a near miss instead of a slightly nearer miss, can steer the system onto diverging trajectories. The laws remain deterministic, but the long-term forecast becomes uncertain because we can never measure every detail with infinite precision. The rogue planet does not need to touch any planet to invoke this regime. It only needs to pass close enough to create strong gravitational coupling with at least one major body. The strongest coupling is likely to involve the gas giants, not because the inner planets are unimportant, but because Jupiter and Saturn carry a large share of the solar system's planetary mass and serve as central nodes in the gravitational network. A close passage near Jupiter is not simply an event involving two objects. It is an event that can rewire the connections among many objects. To understand how that rewiring happens, it helps to see the solar system as layered. In the outermost layers are distant comets and icy bodies, lightly bound and easily disturbed. In the middle are the giant planets and their moons, heavy and influential. In the inner layer are the terrestrial planets, where orbits are tighter and the sun's grip is strong. Normally, the layers interact in a controlled way. The giants shape the flow of comets. The inner planets remain relatively sheltered. And resonances and long-term cycles modulate the system without tearing it apart. The rogue planet threatens to break that controlled flow by forcing an abrupt change in the giant's configuration. One of the most important concepts here is the gravitational encounter itself. When two massive bodies pass near each other, they do not merely tug. They exchange orbital energy and angular momentum. Angular momentum is the measure of rotational motion in an orbit, and it is conserved in isolated systems. During an encounter, energy can be transferred between the body's orbits while the total remains conserved. If the rogue planet is massive and its passage is close, the exchange can shift the orbit of a giant planet measurably. Even a small shift can matter, because the solar system's stability depends on the relative spacing of orbits and on the timing of gravitational interactions. If Jupiter's orbit changes slightly, then the locations of its resonances move. That is not a distant theoretical point. Resonances are the corridors through which instability travels. A resonance can act like a pump, gradually increasing the eccentricity of a small body's orbit until it crosses a planet's path. In that sense, resonances are not just patterns, they are mechanisms. Move the mechanism, and you change which populations are affected and when. Now add a second mechanism, the possibility of the rogue planet itself entering a resonant relationship with one of the giants during the flyby. A resonance does not require a permanent orbit. During a close encounter, if the timing is right, repeated gravitational tugs can occur over multiple passes in a short time, especially if the rogue planet's trajectory brings it through regions where it lingers relative to the planet's motion. This can enhance the energy exchange, turning what might have been a mild disturbance into a stronger one. Models indicate that such interactions can sometimes push a system across thresholds where long-term stability is compromised. That phrase, compromised stability, can sound abstract. Here is what it can mean in concrete terms. The planets do not need to collide for the solar system to be profoundly altered. They only need to undergo close encounters that change their orbits. A close encounter between planets is rare in the current solar system because their orbits are well separated and largely coplanar, not meaning they share nearly the same orbital plane. But if the rogue planet's passage increases a giant planet's orbital eccentricity or inclination, then over long time, the geometry can evolve toward closer approaches. A giant planet on a slightly more eccentric orbit can come nearer to its neighbors at certain points in its path. That increases the strength of their interactions. Those interactions can, in turn, alter the orbits further. This is a feedback loop. The rogue planet provides the initial kick. The planet's mutual gravity can amplify it. In the outer system, the most vulnerable pair is often considered Uranus and Neptune, not because they are weak, but because their masses and spacing make them more susceptible to significant changes during a disruptive episode. If their orbits are altered enough, they can enter periods of heightened interaction with each other and with Saturn. A chain of interactions among the giants can follow, potentially leading to one of several outcomes: a reshuffling of orbital distances, an increase in eccentricities and inclinations across the outer planets, or, in the most extreme cases, the ejection of a planet from the solar system. Ejection is not a dramatic flourish. It is an energetically plausible outcome when large bodies exchange energy through close encounters. To eject a planet, you must give it enough speed relative to the Sun that it becomes unbound, escaping on a one-way trajectory into interstellar space. This is difficult in the current stable configuration, but during a period of strong interactions, it becomes possible. We know such processes can happen because they are among the leading explanations for why many planetary systems observed around other stars, appear to have experienced migration, scattering, and instability. Our solar system's present calm may be the outcome of an early era of violence that eventually settled. A rogue planet entering now would be an attempt to reopen that era. Even if no planet is ejected, a significant orbital shift in a giant planet can transmit consequences inward. Jupiter's role is again central. If Jupiter moves slightly closer to the Sun or slightly farther away, if its orbital eccentricity increases, then the gravitational environment of the asteroid belt changes. The asteroid belt is not a solid ring. It is a population of countless bodies in a region shaped by Jupiter's resonances. Change those resonances, and you can destabilize asteroids that were previously in stable niches, nudging them onto paths that cross Mars and Earth. These changes can unfold over thousands to millions of years, but the trigger can be abrupt. The inner solar system also has its own delicate balances. The terrestrial planets interact gravitationally, and their orbits can be chaotic over very long spans of time, even in the absence of an intruder, with Mercury's orbit often cited as a potential source of long-term instability. This does not mean Mercury is likely to crash into the Sun tomorrow. It means that over billions of years, small uncertainties can grow, and there are small probabilities of dramatic outcomes. If a rogue planet perturbs the giants and shifts the background gravitational forcing, it could alter the statistical landscape of these long-term possibilities. In careful language, it could increase the likelihood of inner-planet orbital changes over geological time, though the magnitude would depend on the specifics of the encounter and would require detailed simulation. But a documentary does not live only in geological time. It lives in the tension between what can happen soon and what might unfold slowly. So we narrow the lens to the period around the closest approach. As the rogue planet passes through the realm of the giant planets, the solar system enters a phase where many objects are simultaneously being scattered. Small bodies are the most visibly affected. Comets and icy objects are flung onto new orbits, some crossing the paths of moons, some grazing the giants' atmospheres, some being captured temporarily and then released. Every such scattering event generates debris. Some objects fragment due to tidal forces, which are the differential gravitational pulls that stretch an object when one side is pulled more strongly than the other. Tidal forces can tear apart a comet if it passes close enough to a planet, turning it into a trail of fragments. That trail can become a stream of meteoroids, small particles that later intersect planetary atmospheres as meteor showers. The sky can become busier, brighter, more active, not because the rogue planet brings light, but because it brings instability. Meanwhile, the planet's moons experience their own risks. Many moons orbit within stable gravitational zones around their planets, but stability depends on the planet's orbit and on the gravitational environment around it. If a giant planet's orbit changes, the balance between the planet's gravity and the Sun's gravity shifts slightly. Some distant moons, especially irregular moons that orbit far away and often on tilted or even backward paths, can become less secure. They can be lost, flung into new solar orbits, or driven into collisions with other moons. Such collisions can generate rings or debris clouds. These are not guaranteed outcomes, but they are plausible pathways through which a rogue planet's passage could alter the appearance of the outer planets, potentially leaving long-lived signatures. At this point, it is tempting to imagine a single defining event, one catastrophic encounter that decides everything. In reality, the danger is often distributed across many near misses. Gravitational dynamics can make a system behave like a set of tipping dominoes, where the exact order matters, and tiny differences decide whether a particular domino falls. This is where cinematic tension can be honest. The suspense is not manufactured. It is built into the physics of sensitivity. A rogue planet's closest approach might be measured in tens of millions of kilometers, or it might be closer. If it passes closer to one giant than another, that one becomes the primary conduit of change. If it passes between giants, the situation can become more complex because the intruder can interact strongly with more than one massive body in sequence. Each interaction can adjust its trajectory and speed, changing the conditions for the next interaction. With this sequential coupling is one reason prediction becomes difficult. To forecast outcomes, you need to model not only the initial path, but also how that path changes after each gravitational exchange. This leads to a chilling possibility that remains scientifically grounded. The intruder's path could be altered in a way that brings it deeper into the solar system than originally expected. An early set of observations might indicate a passage that stays in the outer regions, but a strong interaction with a giant planet could bend the trajectory inward. The likelihood depends on geometry and speed, and in many scenarios, the intruder simply swings through and leaves. But the mechanism exists. Gravity can redirect. In that case, the solar system's danger would not be limited to a delayed comet influx. It could become immediate and personal, because the intruder would now be moving toward the inner planets. If that inward redirection happens, the nature of the encounter changes. The inner planets move faster and are closer together. The Sun's gravity is stronger. A rogue planet passing through here would experience a faster change in direction as it swings around the Sun, and its gravitational influence on Earth and its neighbors would be stronger due to proximity. The most direct risk would be orbital disruption. Earth's orbit could be stretched, making it more eccentric. It could be tilted slightly, altering the balance of seasons. In extreme scenarios, Earth could be nudged inward toward a hotter orbit or outward toward a colder one. These are not the most likely outcomes across all possible flybys, but they are within the range of what gravitational mechanics permits if the intruder's mass is high and the passage is close enough. Even without shifting Earth's orbit dramatically, a close passage could perturb the Moon's orbit. The Earth-Moon system is a gravitational partnership. The Moon stabilizes Earth's axial tilt over long periods, helping keep climate variations within a range that has been favorable for complex life. If the Moon's orbit were altered significantly, Earth's rotational stability could change over time. Again, the magnitude depends on proximity and mass, and responsible wording matters. It is credible to say that a sufficiently close passage by a massive intruder could perturb the Earth-Moon system. It is not credible to claim that such a perturbation is inevitable without specifying a scenario. What the science does allow us to say with confidence is that the rogue planet's passage introduces a phase where multiple outcomes are possible, and where the difference between them can rest on small details. That is the essence of the dice roll feeling, not randomness in nature, but uncertainty in our ability to predict, because measurement and modeling have limits. In a real-world response, this would be the moment when simulation teams run countless scenarios, varying initial conditions within the range of uncertainty, generating probability distributions rather than single forecasts. The question would shift from what will happen to what is likely and what are the worst credible outcomes, and it is here that the narrative pressure naturally climbs. Because once you accept that the solar system's stability can be nudged into a more chaotic regime, you realize the rogue planet's departure does not necessarily end the danger. The intruder may leave, but it can leave behind a system that is now set on a new trajectory, where resonances have shifted, populations have been redistributed, and long-term interactions have been rewired. The flyby is not just a moment, it is an edit. And the next question, the one that carries us forward, is what that edit looks like after the intruder is gone. Does the solar system settle into a new equilibrium, bruised but intact, with changes that astronomers can map and future generations can live with? Or does it enter a prolonged aftershock, where the consequences arrive in waves, comet showers, orbital drifts, and slow destabilizations that only reveal their full meaning over time? Because the most haunting part of a rogue planet encounter is not necessarily the day it passes closest to the Sun. It is the years and millennia that follow, when the sky looks normal again. But the solar system's pathways have been quietly rewritten, and the consequences begin to arrive on schedules no one can easily cancel. When the rogue planet finally recedes, there is a temptation to treat its departure like an ending. The calculations show its trajectory bending outward. The dot fades in telescope images. The headlines soften. The public attention drifts back to familiar skies. But gravity does not offer clean conclusions. A flyby is not a single event that happens and vanishes. It is an exchange. The solar system gives and takes momentum, rearranges energy, and then continues forward with whatever new configuration it has inherited. The most honest way to describe the aftermath is to think in terms of signatures. A signature is not a dramatic scar you can point to immediately. It is a persistent pattern that reveals what happened, sometimes slowly, sometimes in delayed waves. After the intruder has gone, the solar system may look nearly the same to a casual observer, and yet the dynamics can be different in ways that matter. The aftermath is not defined by what we see right away, but by what the orbits now permit. One category of signature would appear far from Earth in the distribution of distant icy bodies. If the rogue planet passed through the outskirts, it could strip away a portion of the Kuiper belt and disturb the edges of the Oort cloud. The Kuiper belt, a region beyond Neptune populated by icy objects, is already shaped by Neptune's gravity and by the solar system's formation history. A rogue planet flyby would add a new layer of shaping. Models indicate that an intruder could tilt orbits, cluster certain orientations, and create populations with unexpectedly high eccentricities or inclinations. Astronomers would not simply notice some objects moved. They would look for patterns that cannot easily be produced by known planets. Those patterns would become a forensic record, a way to infer the intruder's mass, its path, and the distance of closest approach. But the more consequential signatures might show up closer in through time-delayed arrivals. If the rogue planet perturbed the Oort cloud, the solar system could experience a comet shower. A comet shower is not a single wave that arrives all at once. It is an interval of increased comet influx, lasting thousands or even millions of years, depending on how the cloud was disturbed and how the altered orbits distribute arrival times. The mechanism is clear. Comets on the edge of the Sun's gravitational control are easily nudged. Once nudged, they begin long, elongated orbits that bring them toward the inner solar system. They do not arrive immediately because their orbital periods are vast. They arrive gradually, a long echo of a brief encounter. That echo can be dangerous in a statistical sense. Even if impacts remain rare, an increased number of long-period comets passing through the inner system raises the chance of a large impact over the interval. Long-period comets can be large, fast, and difficult to detect early because they approach from far away and may not brighten until they are already inbound. Planetary defense strategies are better suited to known near-Earth asteroids than to a sudden appearance of a massive comet from the deep outer reservoir. So, a rogue planet encounter could shift humanity's risk environment not for a day, but for a long chapter of time. Another signature could be written into the asteroid belt and the population of near-Earth objects. If the rogue planet's passage altered Jupiter's orbit even slightly, the locations of resonances in the asteroid belt would shift. Over time, this could destabilize some asteroids, pushing them onto planet-crossing paths. The timescale here can range from thousands to millions of years, depending on how strongly the resonances shift and how the altered objects diffuse through orbital space. But again, the logic is cause to effect. Change Jupiter's gravitational pattern, and you change which regions of the asteroid belt are stable. When stability changes, the flow of objects into the inner solar system changes. The Moon and the planet's rings could also preserve evidence. If outer planet moons were destabilized or collided, debris could form new rings or modify existing ring systems. Rings can persist for long times, but they evolve. A sudden injection of debris would create a ring with a different particle size distribution and brightness profile. Such changes would not be a sign of imminent danger to Earth, but they would be a visible reminder that the encounter was not a quiet passing shadow. It would have physically restructured parts of the system. Then there is the most intimate signature of all, the architecture of the planet's orbits. The solar system's long-term stability depends not only on the current distances of the planets from the Sun, but on how their orbits interact over time. After a rogue planet flyby, the giant planets might have slightly different eccentricities and inclinations. Those differences would alter the gravitational forcing they exert on one another and on the inner planets. Over long spans, this could adjust the patterns of Earth's orbital variations, which influence the distribution of sunlight and therefore climate cycles. The responsible way to describe this is not as an immediate doom, but as a shift in the background conditions. Earth's climate is driven by many factors: greenhouse gas levels, continental configurations, ocean circulation, volcanic activity, the Sun's luminosity, and orbital variations. Orbital variations are one piece of this system, and they can modulate the timing and intensity of ice ages. A rogue planet that subtly alters the orbital forcing could therefore alter the pacing of such cycles. Whether the effect is large or small depends on encounter specifics. Models would be needed to quantify it, and uncertainties would remain. But it is credible to say the solar system's orbital climate could be altered, and with it, the long-term context in which Earth's environment evolves. There is also the question of whether the solar system remains stable in the strict dynamical sense after the encounter, or whether it has been pushed closer to an instability threshold. Even if the planets do not immediately begin close encounters, the system could become more chaotic over long periods. This would mean that the range of possible future configurations broadens. The solar system might remain effectively stable for billions of years, or it might acquire a higher probability of dramatic rearrangements far in the future. In careful language, a sufficiently strong perturbation could increase the long-term unpredictability of planetary orbits, though the present evidence for exactly how such probabilities change would depend on the details of the perturbation and requires extensive numerical simulation. Now, a crucial branch in this aftermath is whether the rogue planet left entirely or whether it was captured. Capture, as discussed earlier, is expected to be rare because an intruder must lose speed to become bound to the Sun. But if it did happen, the aftermath becomes a different kind of future. Not an echo, but a repeating threat. A captured rogue planet would likely occupy a long, highly eccentric orbit, spending most of its time far from the Sun, and then periodically swinging back through the planetary region. Each return would provide new opportunities for gravitational encounters, scattering events, and resonant disruptions. The solar system would become a stage with a new periodic visitor, and the choreography would never fully settle. Even a captured intruder might not pass near the inner planets on every return. Its orbital plane might be tilted, and its closest approach could remain in the outer system. But the very presence of a massive body on an unusual orbit would reshape the dynamics of distant populations, potentially maintaining a steady trickle of comets and disturbed objects inward. It would become part of the system's architecture, a second sculptor alongside the known planets. If capture did not occur and the rogue planet truly left, then the solar system's future becomes a question of relaxation. Systems can relax after perturbation, meaning that their components settle into a new configuration where interactions become regular again. The planet's orbits could remain stable, the comet influx could rise and then gradually decline, and the system could continue on, changed but functional. In many scenarios, this is likely. The solar system is massive and the planets are spaced in a way that can absorb a certain amount of disturbance without collapsing. But not all disturbances are equal. A close flyby by a very massive intruder could push the system into a new regime where relaxation is slow and punctuated by aftershocks. Those aftershocks could include periods of increased impacts, orbital drift, and changes in the distribution of small bodies that persist long after the intruder is gone. The suspense in the aftermath is therefore not the presence of the intruder, but the uncertainty of what it set in motion. This is where the documentary lens returns to Earth, not as a melodramatic center of the universe, but as a world whose safety depends on the solar system's architecture. And the real vulnerability of Earth is not that it will be pulled directly into the rogue planet's path. The more likely vulnerability lies in the chain reactions, the increased flux of comets, the destabilization of asteroid populations, the potential alteration of long-term orbital cycles. These are risks that do not produce a single cinematic moment. They produce eras. If humanity knew such an encounter had happened, the response would not be purely observational. It would become a long-term project of monitoring and mitigation. Telescopes would track new comets and near-Earth objects. Space agencies would prioritize surveys for incoming long-period comets. The mathematics of orbital prediction would become an everyday tool of risk assessment, and the encounter would change not only the solar system's dynamics, but also the priorities of a civilization that now understands, in a visceral way, that celestial stability is not guaranteed. And there is one final signature that is less physical and more philosophical: the evidence that the solar system is part of a larger, restless galaxy. A rogue planet flyby would be a reminder that interstellar space is not empty. It contains worlds that have been ejected, planets that formed without stars, and objects on trajectories shaped by the Milky Way's gravity and by past encounters. Our solar system, which feels like a closed family of planets, is embedded in that flow. Over the age of the Sun, it has likely experienced close stellar passages and may experience more in the future. A rogue planet entering the solar system would be extreme, but it would not be a violation of cosmic law. It would be an example of it. So what happens if a rogue planet enters the solar system? If it passes far away, it may leave behind subtle reorganizations of distant icy populations and, potentially, a delayed increase in cometary arrivals. If it passes closer, it can redirect reservoirs of small bodies inward, raising the long-term impact risk. If it perturbs the giant planets, it can shift resonances and alter the stability landscape, changing the pathways through which asteroids and comets travel. In extreme cases, it could push the system toward long-term instability, and in rare scenarios, it might even be captured, becoming a new, enduring gravitational actor. The mechanics are not mysterious. They are the plain consequences of gravity. Mass shapes trajectories. In trajectories shape encounters, and encounters reshape the system. The uncertainty is not whether gravity works, but which configuration the solar system would land in after the exchange, and how long the echoes would last. And that is the lasting tension the rogue planet leaves behind. Even after it vanishes into the dark between stars, the solar system would carry a revised set of possibilities. The sky might look the same on a clear night, the constellations unchanged, the seasons still turning. But beneath that familiar surface, the orbits would remember. They would remember in the slow arrival of comets from the deep cold, in the shifted resonances that guide asteroids, in the subtle modulation of planetary cycles. A transient visitor, gone in a geological instant, could still leave behind a solar system that is, in ways that matter, permanently different.